our second
We're coming to the second lecture.
Hi.
So today, last time we saw a kind of informal definition of high-dimensional expanders. So today we'll make it more formal, and then we will prove the trickle-down theorem. So by formal definition, I just mean that we will introduce weights on all the faces because our complex may not be regular. And finally, we will look at higher order random walks. Okay, great. So many of you said you're familiar with weighted graphs. So let's start with just defining what a weighted graph is and how it induces a weight on the vertices and how the spectrum is defined with respect to that weight. Okay, so let's say we are given a graph G on vertices V and edges E with a distribution pi 1 on the edges. Then this distribution pi 1 induces a natural distribution pi 0 on the vertices. And the distribution is what you might guess. To sample a random vertex V from pi 0, you sample a random, or the distribution pi 0 first samples a random edge E from pi 1, and then outputs a random one U or V with probability half each. So this is what you get. So you get a distribution V on the vertices. And now we can define define the spectrum of G with respect to this distribution pi 0. So firstly, we'll define the adjacency matrix of G at an entry UV, it's the probability of transitioning from V to U. So it's defined as the conditional distribution on the edges that V sees in the link, V sees in its link. So it's going to be pi 1 of UV divided by the sum over W in the neighbors of V, pi 1 of VW. And just note that when you have suppose you have the uniform distribution over the edges of G, what you will get is just a uniform distribution. This will just be 1 over the degree of V, and also pi 0 will just be proportional to the degree of V. Okay, so any questions about this?
Pi 0 is just the sum of pi 1 over the edges touching V, proportional.
Exactly, so let's just write it out. Oh. So this is the usual case of irregular graphs.
And if the graph is regular and pi 1 is uniform?
Yes, and if it's regular, the case that we studied last time, pi 0 is also uniform. All the conditional probabilities are also uniform. Okay, and now with respect to pi 0, we can define the spectrum. So what that means is we first define an inner product. We look at the inner product with respect to pi. So this means, so f dot g with respect to pi 0 is just equal to summation over u in the vertices, pi 0 of u, f of u, g of u. And now with respect to this inner product, you have that A is self-adjoint. A of 1, the vector 1, is equal to 1. And also lambda 2 of A is equal to max over all functions perpendicular to the one vector of A of f AF in the pi 0 norm FF. Okay, so any questions about this? And given this, we say that G is a lambda spectral expander if lambda 2 of the adjacency matrix that we just defined is at most lambda. And equivalently, this is like saying that A minus the matrix J, which I'll just define, is PSD less than lambda times identity, where J is just the matrix which has the distribution pi 0 in all its rows. So when you have a uniform graph or a deregular graph, this matrix is just 1, 1 transpose by n. Okay, great. And now the way we got a distribution over vertices from the edges, we can do the same thing for simplicial complexes. And today we will just look at, it will suffice to look at two-dimensional complexes. This captures all the intuition for higher dimensions. So let's imagine we have our triangles in this layer. And these are the edges and vertices. So we will equip our complex with pi 2, which will be usually a uniform distribution over the triangles. And that will induce a distribution pi 1 on the edges, where pi 1 of any edge, where pi 1 is again just defined as pick a triangle UVW from pi 2, and then pick one of the pairs UV, VW, or UW with probability 1/3 each. So that gives you a distribution pi 1. And then once you have pi 1, you get the distribution pi 0 from pi 1 in the same way. And again, the way we define conditional distributions here, we can do the same thing for links or neighborhoods in this complex. So let's see what's the conditional distribution in the link of V. So the complex xv is just a graph because this is the vertices and these are the edges. So when we think of pi2 as a uniform distribution, can someone say what is the distribution we get over the edges in the link of V? Sorry. So you will just get back the uniform distribution in the link of V. So let's be more formal. So pi, we will denote this distribution in the link of V as pi V. So pi V1, which is denoting, we'll just drop this subscript. So pi V of an edge in its link, suppose UW is an edge, is just going to be defined as pi 2 of UVW divided by sum over all triangles that belong to the link of V, or all triangles that contain V. Over U prime U prime W prime V. And so if this is the uniform distribution, you will get back the uniform distribution in the link. And similarly, you can write down the distribution over vertices in the link, which is going to be the exact same thing.
So that's just the probability of UVW conditioned on V being in the triangle, or no?
Yeah. So these are just conditional probabilities by conditioning the measure pi2 lying inside the link of V. Okay, and now with these definitions, we can define two-dimensional HDX more formally. So let's also call the adjacency matrix of this graph AV. So firstly, we want all the vertex links to have eigenvalues at most lambda. So this is like saying all the vertex links, the graphs in them are expanders. And finally, we want this graph, the base graph of the whole complex, to be an expander. So the graph x0, x1, vertices, edges with respect to the distribution pi1 over edges is a lambda expander. We'll call the adjacency matrix of this guy A. So lambda 2 of A is at most lambda. Okay, so any questions up till now? Yeah. Yeah, so this is just a two-dimensional HDX. I'm going to focus on 2 dimensions for the talk so that we avoid. Oh, sorry, yeah, this is.
Capital.
Yeah. And if you want d-dimensional HDX, you'll have all links up to d minus 2.
Actually, I have a trivial question. When you define the adjacency matrix, suppose I take pi 1, just the usual thing.
Mhm.
So A is, BW is like 1 over the degree of B. Then it is not self-adjoint for the general case.
Yeah, so we,
But here you say there, A is
With
self-adjoint.
respect to
oh
the
yeah, this
inner
is
vertex.
all with respect to, yeah, that's a good question. This is with respect to pi 0.
With respect to
That
that inner
the inner
product.
product.
Yeah,
Yeah.
this.
With respect to inner product.
Yeah, sorry, yeah. Yeah, so if I forget to label the inner products, every time we look at inner products, they will be with respect to the norm in context. Any more questions? So in general, this can be the uniform distribution, but suppose there are some edges that are not contained in the same number of triangles, then pi 1 will not be the uniform distribution. So we do need to look at all of this distribution stuff because the complexes we have do not have all these pi i's being uniform. Okay, great. So now we will prove the trickle-down theorem. So this is a theorem by Izar, who's also in the audience, which says that once you have condition 1 and this graph is connected, so all you need to look at is x0, x1. As long as the graph is connected, you can bound the eigenvalue of the graph with respect to the inner product pi 0. Okay, so let's state it formally. So suppose it's one skeleton, which is just the base graph, is connected. And for all we the eigenvalue of the normalized adjacency on V is at most lambda. You get that the one skeleton of X, or the graph, the adjacency matrix of the graph x0, x1, pi 1 has lambda 2 of A at most lambda by 1 minus lambda. So as long as lambda is strictly smaller than half, this number will be strictly smaller than 1. And also note that we do require the one, this is a minimal, like necessary and sufficient condition, because if this is not met, then you could take the union of two complexes, and that's not going to be that's not going to satisfy lambda 2 of A smaller than 1. Okay. Okay, so let's prove this theorem now. First, we'll start by noting a very important fact, but not too hard, which is not too hard to prove, which is something about how these distributions pi i's behave. So, first fact is that the distribution, these two distributions are equivalent. So the first distribution D1 samples a random vertex V from pi 0 and V or U from the link of V. So it samples it from the distribution pi V and outputs U. And the second distribution samples an edge VU from pi 1, which is distribution on edges of the complex, and outputs U. So you, even just like the case in irregular graphs, you can check that these two are the same. You could do the calculation, which I won't do, but this is quite easy to check. Yeah.
Exactly with it outputs U, it outputs at random one of the two vertices of the edge.
Oh, right. Yeah. Sorry. Yeah. So this is. So the distribution D1 is equal to D2. So this gives you the same distribution over the vertices. So any questions about this? And similarly, you can do this for higher faces, or let's do this for edges. So the first distribution D1 samples a random vertex from pi 0 and an edge in its link. And outputs the edge. Yes.
So are both of those distributions just the same as pi 0?
Yes. So that's the claim, that they are the same because the marginal. So the way we defined pi 0, we take a random edge from pi 1 and output U. So they are both. Oh yeah, we should just see that they are both equal to pi 0. And this is exactly how we defined pi 0. So here in the second. There are two ways to sample. This was two ways to sample a random vertex. We can have two ways to sample a random edge. So the first way is more complicated. What it does is samples a random vertex, samples an edge in the link of the vertex, and then outputs that edge. And the second distribution samples a random triangle UVW and outputs UW with probability 1/3. And we know just by the way we defined pi 1, this is the same as the distribution pi 1 on edges. And the claim is again that D1 is equal to D2 is equal to pi 1. Okay, and given these two facts, Yeah.
The second poly means that the global distribution pi1 is like a convex combination of sampling a vertex and then the local distribution inside the local vertex. First thing, this global thing is a bunch of local.
Yeah, so what Reed just said is that the global distribution pi1, you can get it by many local moves, by just sampling a vertex and then sampling something locally inside its link. And that's what we are going to use to prove this local to global theorem. So what you can easily derive from this is the following. Expectation over V from pi 0 of F. Okay, so let F and G be functions on x0 to reals, and let Fv and Gv be their restrictions. To the link of V. So what this means is that Fv of u is just equal to f of u for all u in the link of V. Okay, so what we get is expectation over V of the inner product of Fv with Gv. So this is an inner product with respect to the distribution pi v in the link. This is equal to just the global inner product of f and g with respect to pi 0 on the vertices. So why this is true is because this distribution, we can rewrite this as expectation of V, expectation of U in the link of V. So expectation of U of f of U times G of U. So this is the process where you sample a vertex and another vertex U in its link, which is the same as sampling vertex directly from the pi 0 distribution. So this is just the same as expectation over U f of U G of U. Okay. So here we use the first fact, and the second fact gives us the following. So again, we sample a vertex and we look at AF, AV, FV of GV. Again, with respect to the norm on V. This is the same as the global thing where we simply remove all the V's. So it's the same as AF G with respect to pi 0. Oh, sorry, I won't write below this. Okay, so any questions about this? Should I expand this out or?
I always just to make sure the trickle down becomes an interesting theorem and only like when lambda is less than half or more than half or something like that.
Yeah, if lambda is more than half, then this becomes 1, which is a trivial fact. So it's only useful if lambda is strictly smaller than.
later to one of the identities Siddhant wrote down?
Yes. So in fact, Siddhant was using this fact where he said that you sample a vertex and then you look at an edge in its link. That's the same thing as just directly sampling an edge over the whole distribution.
The point is this holds in some greater generality than Cayley graphs.
Yes, as long as we look at the correct distributions.
What is AV there? AV?
Oh yeah, AV is, okay, I erased it.
So like
AV
the
is the,
matrix of the mean
yeah,
Yes.
with the appropriate weights.
yeah.
So like Siddhant showed, like, as I could understand it, was showing trickle down as a way to prove graph expansion. But you're kind of claiming that I should think of it as like when I can apply trickle down, in fact I have a two-dimensional expander in hand.
Yes. So Siddhant, in fact, did show the same thing, I think.
A is an adjacency matrix of a graph, so this is showing graph.
But I'm saying like it's kind of morally speaking more than that I actually have
Yeah.
a two-dimensional expander. What you're saying.
Yes.
Technically don't have to use you could define other distributions on triangles besides like the natural one that you get just from looking at all the triangles in the graph. I guess hypothetically you could maybe prove expansion without using all the triangles in the graph or something.
But maybe what is it for something to be a two-dimensional expander? It's all the links are expander graphs, and the one skeleton is an expander graph. You're starting with the assumption that all the links here are expanders, and so to get a two-dimensional expander, you just need to just get expansion of that one additional graph.
Yeah.
Yeah, which you
And
get.
that's what this is
by-
giving. It's saying.
I'm just saying, like from Siddhant's talk, I thought of it as like a technique to prove regular graph expansion, but this technique is special because when you can use it, it's in fact coming from a two-dimensional.
Yes,
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 yes.
yes.
In fact, yeah. People never used to talk about this as a technique for Fourier expansion until we discovered that these things exist. It didn't seem like something that even is worth.
No, because from the group theory side, I know it was proving property.
That's Juke's paper.
Yeah, but I'm saying in fact it's something like in degree.
Yes. Yeah. So I'll just I won't prove the whole thing here, but the basic observation is that AV FVGV is equal to expectation over the edges in the link of V, F of U times G of W. So again, the first thing is looking at the distribution D1, which samples a V and an edge in its link, whereas the second quantity is directly looking at an edge.
Can you maybe shift the word because we don't see the most important part?
Oh, yeah. Oh. But it does, this one doesn't shift, so yeah. Which? Oh, okay. Oh, yeah. Yeah. Okay. Okay, magic. Okay, this is the, in fact, most important identity we'll be using to prove the trickle down. So A is the adjacency matrix of the full graph. And let's analyze some eigenvector, which is the, let's say it's the second eigenvector F, which is, okay, So let f be perpendicular to the all ones vector, again in the pi 0 norm, pi 0 inner product. And let norm of f in the pi 0 inner product be 1. And given that f is an eigenvector, we have af is equal to gamma f. And we want to prove that gamma is small. Okay, so the first thing we do is to look at the restriction of f in every link. So let fv be the restriction similar to what we did there. And similar to many spectral graph theory proofs, we will break fv in its component parallel to 1 and perpendicular to 1. So let's write fv as fv parallel plus fv perpendicular. And actually, we know what fv parallel is. So fv parallel is just the inner product of f with all ones, or inner product of fv with all ones times all ones. This is again in the link of v. And this quantity is just an expectation of u taken from the link of v of f of u. So do we know how to simplify this further? Like what should this be? So this is just, sorry?
Is it AF of V?
Yeah, so this is exactly the transition matrix A applied to F at the entry B. Because these are exactly the probabilities of transitioning from V to U. And we also know that AF of V is just going to be gamma times F of V. Okay, and now given this, it's quite simple to finish the proof. So firstly, we have that expectation V of Fv parallel squared. This is just going to be gamma squared Fv squared which is just 1. Oh, yeah. So since norm of f is 1, we just get this is gamma squared. And because of this, the perpendicular is going to be 1 minus gamma squared. Okay, and now let's look at AF. This is, we want to show that this is smaller than a lambda by 1 minus lambda. So this guy, by definition, is equal to lambda, gamma. And now we'll use this identity. So we'll break up the global function into its local functions. So it's an expectation over v taken from pi 0 of AV, FV, FV. which is so this is gamma squared. Like the parallel part has eigenvalue 1 with respect to AV, and the perpendicular part remains. But now we know that all the links have eigenvalue at most lambda. So this is going to be at most lambda times the norm of FV. Perp. Sorry? Oh, yeah. So this is at most lambda times the norm of expected norm of FV perp squared, which is gamma squared lambda times 1 minus gamma squared. Okay, so what we have gotten so far is gamma is at most lambda. Sorry. So gamma minus gamma squared is at most lambda into 1 minus gamma squared. And now we will use the fact that gamma is smaller than 1. Okay, maybe. So given that gamma is smaller than 1, you can divide out by 1 minus gamma to get that gamma is at most lambda by 1 minus lambda. So the last step is just a calculation. Yes.
Here it seems that you only use that most links are good expanders. Is that not?
We did use.
Expectation over V.
I think it does matter, like that you want all links to be.
Because it could be, in the worst case, that all of the weight is on the particular local component. Like all the mass of FV happens to be on a bad link, and then you wouldn't be able to bound it by. So it's using a worst case.
Yeah, we are using that every link is smaller than, every eigenvalue in V is smaller than lambda.
But you take expectation over V, right?
Yeah, but then, each inner product in some sense has to be small. Because there could be a lot of weight on, like what Max just said, there could be a lot of weight on links which are bad expanders.
The eigenvalue will be 1 at most in the first case, for like bad links.
Yeah, so maybe if your distribution over the like pi 0 has small weight, that might be fine, but not all.
But even, think of an example where you take two HDXs and you connect one vertex from each of them, and just that link will be problematic.
Yeah.
The graph is not an expander.
Yeah. But, okay. Yeah. Okay, any more questions?
There's no bound on the norm of f sub v, right? That can range very widely.
Yes. Yeah.
So even if it's only on a small part of pi 0,
right.
you won't
That
be able
will
to
skew up.
discard
We
it.
don't have control
Yes.
over F.
Yeah.
Talks on expanders, there was this interpretation by relating the square of the Laplacian to the Laplacian. Is there some interpretation of this as relating the square of the Laplacian
When I spoke to Siddhant, I think the main part of why he used the square was to just make it a sum of squares, compatible with sum of squares, so that the inequality looks like a polynomial.
The gamma squared term is coming from AF. The parallel term ends up being coming from the two-step wall. Because it's F parallel, which is AF.
Yeah, you can write a
You are
degree
correct.
2 sum of squares proof for this.
Maybe I can try. One can present this proof that way. So if you, the thing that happens in these Laplacian solvers is you sparsify the square of a graph by replacing all the cliques with expanders, and you get spectral approximation of the square. And so something having all the links be expanders is, as I think Siddhant said, tells you that the graph, the global graph, is a spectral approximation of its square in the usual Spielentime sense. And use that to.
Okay, any more questions?
Yes.
Oh.
Is there any analogous combinatorial? I mean, I guess you get something just comparing.
Yeah.
Well, the combinatorial really means all these neighborhood graphs, i.e. control point, right? All the neighborhood graphs. It's actually very much related with, clustering correlations.
There's the local to global theorems for.
Yeah, but I don't think they mean. There are local to global theorems for the combinatorial generalization, but I'm guessing you mean that if all links are combinatorial expanders. Do you get that? Yeah. I'm not sure. I think you could just translate.
Next week, Siki will talk about the other notion of expansion, which you might think of as more combinatorial. And also there you have these local to global. Being combinatorial, they're harder to prove.
Yeah. But that, okay, yeah. There could be two interpretations of the
combinatorial.
Yeah. Okay, so with this, now this gives us a way to prove that a complex is a high-dimensional expander. In general, we wrote this for 2D, but you can iterate it, and what you'll get is a statement in higher dimensions. So if all links have connected one skeletons, and all d minus 2 links of X are lambda spectral expanders. Yeah, all one skeletons. Okay. Then X is lambda by 1 minus d minus 1 times lambda local spectral expander. So this just means that all links of X below d minus 2 are have their one skeletons which expand. And you just need to apply this theorem again and again to get this. So this tells you that to show local spectral expansion, all you need to do is bound the topmost links and also show that every other link is connected. Okay, with this, I will end the discussion with some discussion about higher order random walks. So suppose we have an HDX, like these are all the D faces and so on. We might want to look at random walks between these levels. So what that means is, let's say we want to look at a graph whose vertices are the k faces of this complex, move to a random I face below it, and go up to a random k face containing this I face. So when we move down, what we do is just take a uniformly random I face contained in the k face. And when we move upwards, we move according to the conditional distribution that we defined earlier. So we look at all the faces that contain tau, conditioned, with respect to the probability measure pi k, and then we move upwards. And we might want to look at what are the eigenvalues of this random walk. So this might look contrived, but even for the complete complex, this generates the so-called well-known Johnson graphs. So let me just tell you what these are. So the Johnson graphs have their vertices being all k size subsets of the universe on n. And you have an edge between two sets S and S prime, such that S and S prime intersect in exactly I vertices. So these are very well known, and there are many textbooks that analyze this spectrum of these graphs. So one way you could try to analyze the spectrum is to actually diagonalize the adjacency matrix, find its eigenvectors and eigenvalues. But this machinery that we just discussed actually gives you a very nice and generalizable way of analyzing the spectrum of these graphs. And in fact, all random walks on any high dimensional expander. So let me again just say what happens for two-dimensional complex. And also, okay, I'll just write down what is the eigenvalue of this random walk. It's going to be something like I plus 1 by k plus 1. And if x is a lambda spectral expander, there'll be some error term that depends on lambda. So for example, for the complete complex or for the Johnson graphs, you can just use this plug in lambda equals 0, and you get a upper bound on the eigenvalue. This is the eigenvalue of the Johnson graph or the random walk that goes down and comes.
If lambda is
If x is a,
lambda HDX.
yeah. And quickly we'll talk more about these walks, like they come up in natural Markov chains, such as sampling spanning trees of a graph. You can show that you can build a complex out of it, show that complex is a lambda HDX, in fact a 0 HDX for spanning trees, and then simply like use these theorems, this very generic machinery that shows that the eigenvalues have this form. Yeah. Yes. Yeah. We are thinking of lambda being really small, like 1 over poly k or even exponential in k.
So sub k does hide something?
Yeah, this is, I can just write it. It's at most quadratic in k.
Lambda is 1 over exponential.
Yes, you can think of that.
We will probably give a more general form. It's non-trivial for any lambda less than 1. The real form is like I plus 1 over k plus 1 times some product, like 1 minus lambda to the k, like of the gaps as you descend.
Yes.
And how do you obtain the Johnson graphs if you have the clique as your complex?
Yeah, that's a great question. So for the Johnson graphs, you can just take this to be the complete complex. That was our first example of an HDX. So what we have is these are the D faces, which are just going to be n choose D. All n choose D or all D size subsets. Kth level will have all k size subsets. So that will be your vertices. And you put in an edge exactly when there's a way to go up and down to that set. So you'll exactly get edges when they intersect with some particular size, intersection size. Okay, any more questions?
I mean, there's a chance when you go back up, you'll have a little more overlap.
Yeah, the chance when you go up and getting an overlap is really small, so that's going to be like negligible. I'll end with a quick comment on how this is proved. So just like we had these normalized adjacency matrices, we can define a normalized or like operators on these on HDX. So let's just look at x1, x2, and x0. You can define an operator that takes functions on the vertices up to functions on the edges. So what it does is just take on an edge uv the function g or the function up of f. At an edge uv just averages the two values of f. So that's just going to be f of u plus f of v by 2. And a down operator that takes functions on edges down to functions on vertices. So what this operator does is to define a value on a vertex. The vertex looks at all its neighbors and averages it according to the conditional distribution. So this is very close to, this is just going to be expectation over v in the link of u of f of u. This is like very close to the usual adjacency of v. Oh, right. This is very similar to the normalized adjacency matrix of the graph.
It is like unsigned.
Yes.
Take out the signs.
Yeah. And usual spectrum, or this is just a graph, x0, x1. So the spectral, just the spectrum of the graph, like if the graph is lambda, lambda spectral expander, that can be actually interpreted as saying that the adjacency minus the all ones, or like the pi, the constant matrix is PSD less than lambda times identity. This actually turns out to be equivalent to saying that the random walk that goes up and down, the non-lazy version of that random walk minus the random walk that actually goes down and up, which is like some kind of trivial random walk, is at most lambda times identity. Okay, I should have like numbers here, but yeah.
Maybe this is already pretty.
Yeah. So finally, like I'll just end with saying that this is an identity that generalizes at all levels. Basically, what you get is going up and down is the same up to some laziness factors as going down and up, and you can get the spectrum of all of these walks.
As a mathematician, I should think of like analyzing this, like edge triangle to edge walk, or vice versa, as analyzing the spectrum of like not necessarily the Laplacian, but like only dB star or D star D.
It's a signless version of the Laplacian.
It's the what?
A signless version. You don't have orientation. So
a signless.
There's no sign.
yes. So it's the signless Laplacian.
You take out the signs.
But it's like only like instead of going, like if I only do up and down, then it's like dB star and not dB star plus D star D.
Because it doesn't have sign, it's not the same.
Yeah, no, it's a different order.
Okay, thank you.